Okay, dear colleagues, hello everyone. I invite you to session 6, machine learning methods and applications. So according to some organizational features, I have to start with this session and welcome Andrey Parinov to give the first talk on this session concerning the consensus clustering methods. And after that, Andrey will grab my duties as a chair of this session. So Andrey, you're welcome.
Okay, thank you. Okay, I will start. Well, my name is Andrew, and this work was done with Boris Mirkin. He's the leading research, also senior research fellow in our university, and I'm right now I'm chief expert actually, and a research fellow in a laboratory of data analysis. Okay, so this talk is devoted our new method for constructing consensus algorithm, and the goal of this paper is to present and justify a self-adjusting method for finding a consensus partition over a partition ensemble. The method is basically conventional locally optimal and algorithm of clusters over the consensus matrix, supplemented with several traits. So the traits include shifting the similarity values to a zero sum, the semi-average within cluster criterion, and zeroing the diagonal similarities at each agglomerative step. So let me say the several definitions. We have a number of partitions, R1, R2, Rm on a set of n objects, I. And any partition R on I can be one by one represented by its binary adjacency matrix R, such as Rij equal 1 if both objects I and j belong to the same part in R, and Rij equals 0 otherwise. So the consensus matrix A, whose I and j entry is defined as the number of those partitions in which both objects I and j belong to the same part cluster. So this is the basic matrix which we will use in our constructing optimal algorithm for finding. Have a good day. And the main idea of this work is to test several ideas. And the first idea is to use modularity shift. So the modularity shift gives us the different positive and negative values in our consensus matrix. So let's the summary similarities express the respective charge of row I and j, and this will gives us the method to construct the consensus matrix by the following formula. I think the idea of this formula is quite clear. Yeah, what we are doing here. So first we find the sum of rows, and then we find some columns, and then we find the multiplication A I dot and A dot J, and then we divide it to the sum of all elements. So this will gives us the normalized each element in our consensus matrix. Later, I will show the example. And another idea which we will show in this paper, the scale shift. So this the transformation of our consensus matrix based on this formula. So at each element, we will subtract the average element. Okay. So let me show the example of these formulas. So let's have 6 objects, and the table 1 shows the cluster labels for these elements. And the consensus matrix, which we compute as a sum of elements at each partition, shows on the table 2. By the way, you can ask me at any point of my talk. Okay, so we have the consensus matrix, and on table 3 we can see the random interaction matrix in the middle, modularity shifted consensus matrix on the right, and a scale shifted consensus matrix for partitions at table 1. I'm sorry, in table 4. Okay. So let's keep in mind our shifted consensus matrix, and then we have to define the partitioning criteria. This partitioning criteria will be optimized in our algorithms. So the consensus matrix have an entries and AJ are considered as similarities between I and J. Then for any partition R in K parts clusters, we find the similarity, which is scored with the sum of similarities A over all pairs of objects from Rk. So the total within cluster similarity we find by the formula, which is showed on the slide. So it's clear that this should be made as high as possible for finding the best cluster partition. So actually, this is the sum of elements in our consensus matrix, which done by cluster and by our partition. So this is the third partitioning criteria, and also we tested the semi-average partition criteria, which is quite obvious. And actually, well, I cannot just to. I think this would be can to, yeah. I think it would be better. Yeah. So this is the second partitioning criteria. Over our consensus matrix, actually we're finding the sum over all clusters and divided by the number of elements in this matrix. Yeah. Okay. So we have done this. So we have our consensus matrix shifted by two methods and two partitioning criteria. And these basic steps we are using in our agglomerative algorithm, which is doing these steps. First of all, the first step is initialization. Which consists of taking singleton clusters as the initial partition to consist of singletons, and we define the similarity matrix between them, which is equal to A. So B is equal to A. And actually, in our case, this matrix is the same that shifted consensus matrix. Yeah. And the second step for a partition, we find matrix B of summary similarity values between clusters. So as S and T is the iterator over our clusters. So then we find the maximum in our consensus matrix, and if B greater than 0, we merge two clusters and elements in one cluster. Yeah, we find the union, and we are doing the follow-up recomputation of the summary similarity by adding rows for all elements, and we find the sum of column into one column. So after that, we remove one row and column and decrease the number of elements in this matrix by 1. So the algorithm stops if B is lower than 0, and if M, which means the number of minimum elements, lower than 3. So then we stop our agglomerative algorithm. Okay. So actually, this agglomerative algorithm can be modified for using semi-average criteria by this way. The only thing we need to formulate before is the level of criterion change at merging two clusters. So let's consider a current partition and the result of merging clusters S, SS, and ST. So the difference between, so we're finding the difference between two matrices, G and G from ST and G from S, that can be expressed by this formula. So this is the measure which we are finding between our two matrices. Okay. So this we are doing for semi-average criterion for finding optimal criteria for using of agglomerative algorithm. And the other steps actually are the similar. The initialization is the same, and the general step actually is the same, except we are finding not the maximum of element in our consensus matrix. In this version, we are finding the difference between two consensus matrices using previous formula. Okay. So the main advantages of determining the number of cluster by such way that the similarities after the modular shifting or scale shifting is determined automatically by computing stops at that M, which is optimal for these matrices. And actually, the criterion is quite obvious and clear and used in many papers. And also, we, on the testing step, we compare our algorithm with the Louis-Van algorithm, actually, which is quite similar to our algorithms at basic steps. First of all, specify and part singleton partition. And then, at any given partition, run a loop over arbitrary ordering of clusters. Within this loop, we are doing several steps. First of all, at any given S, find T star, maximizing the difference of similarity over all elements. Then we merge clusters RS and RT star together and change R for partition RS and R from S and T star, and decrease number of clusters by 1. Then we check stop condition, either all difference between these matrices should be lower than 0 for S not equal T or K lower than 3. And if it's true, we stop. If not, return to the loop. If the loop is finished, go to second step with current R. Okay. So these 3 algorithms was tested on the synthetic data set. And actually, the procedure for creating synthetic data set using 3 parameters: the size of entity set N, the number of parts in the partition K, and their minimum size M. An ensemble of partitions are to represent it, and we specify a probability P, which shows the probability of mutation. In the follow-up computations, we used 2 values for the number of objects N and 3 values for the number of clusters. and two values for the size of partition ensemble. So the quality of the results is scored by two characteristics: the number of clusters obtained and the score area. So after we generated our synthetic data set, we tested our algorithm, and the results now showed on the table 4, table 6, table 7, table 8, and table 9. So if we look at these tables, we can see that the maximum criteria AREI the maximum showed on agglomerative semi-average criterion, yeah, at the first cluster, at the 4 clusters. So also we can see that semi-average criterion actually show the better result than the summary criterion. It's actually every experiment. And the best result showed at 15 clusters at every every experiment. So the conclusion, you can find that the results at 100 and 300 objects almost coincide, which means that the number of objects under consideration has little effects on the consensus solution. And in contrast to expectations, the results at 2 different normalizations, the modular one and the scale shift, are much similar. So that the question of which one to use gets irrelevant in consensus clustering. And the cluster recovery is always better with semi-average criterion rather than with summary one. The larger the number of clusters, the greater the difference. The greater the size of the ensemble, the result is better. The data recovery results at m equal 10 are considerably worse than at m equal 40. Especially the wasting is the effect at the summary criterion, at which the cluster recovery level is kept on average at area equal to 0.4 at 4 clusters, 0.2 at 9 clusters, and 0.1 at 15 clusters. So at minimum elements, minimum size of ensemble equal 40, agglomeration at the semi-average criterion leads to perfect results at k equal 9, 15, and almost perfect results at k equal 4. The Liouville algorithm at the semi-average criterion reaches almost as good results as in cluster recovery. However, it fails with respect to the number of clusters. In contrast, at number of the size of ensemble equal 10, the Liouville algorithm always wins at cluster recovery, although still overestimating the number of clusters. So there is a method among those under consideration that always recovers the number of clusters correctly, the agglomeration for the semi-average criterion. This works even when AVI decreases to the order of 0.7. The only case at which this might fail, however, slightly, is the case of k equal 15, m equal 10, that is m lower the k at a smaller number of objects. This is the conclusion, and actually that is all. So thanks for your attention. Questions?
Thank you for the presentation.
Okay.
I have a question. Some of your formula remind me GLCM. GLCM stands for gray level coherence matrix. Are there some connections with it in your?
Well, no. We actually using modified Louis-Van algorithm, as I can showed before. Actually, this was the basic algorithm, and we tested our modifications, model shifting, and scale shifting.
Just some similar parts. Okay, thank you.
Okay.
Do we have more questions from the auditory? Do we have some questions from online auditory?
Okay.
It's not showing like. Yeah, it's showing right now. Okay,
It's
so
showing.
yeah, there is no questions.
No
It
questions.
seems-
So,
But
maybe-
just to make sure, like, yeah, there is no.
Maybe one general question, not very close question, but maybe some general question. So
Yeah.
even for this way of this tricky way of clustering, so you provide several subways
Yeah.
to clusterize something. But is it possible to propose, for instance, if you have some new fresh data set, can you provide some recommendation whether is it reasonable to apply your ways of clustering or not, and whether is it reasonable to apply some concrete way of clustering, or should you apply everything and try to compare for every particular data set?
Well, no, actually, this works. Wasn't focused on that question. We only tested 3 algorithms, and the idea that we can use criterion, actually several semi-average criterion, yeah. Actually, this criterion for optimizing in algorithm for finding best partitioning of the initial data set. So the recommendation of using any clustering algorithm was out of the scope of this work. Actually, as you know, there's much more clustering algorithm already, and we was not focused on that.
Okay, thank you. Do we have more questions? Okay, so in this case, I'm glad to pass my duties as a chair to Andrey.
Okay, thank you. Okay, thank you very much. We can proceed.